Humanity is looking for new energy sources. Thermonuclear fusion, in which the nuclei of light atom fuse, could be one of them, but very high temperatures and pressures are needed to achieve it. It's easy to reach such conditions in the cores of stars, but on Earth it is more difficult. Scientists have tried a variety of ways to ignite fusion. Among the most elaborate methods is a device called a Tokamak. Here, charged particles are held by a special magnetic field in the shape of a torus. The Tokamak generates it with toroidal coils. Further, it is shaped by Poloidal Coils and a magnetic field generated by a current flowing through the plasma, which is created by the transformer pulse. Since 1958, when the first Tokamak was launched, dozens of Tokamaks have been built and operated, achieving many insights and successes. They have reached fusion, but never gained more energy than was expended to ignite it. A larger plasma volume has been shown to improve plasma parameters. Currently, the world's largest Tokamak is the JT60SA, with a volume of 130 cubic meters. But a much larger plasma volume will be needed to successfully ignite fusion. The ITER Tokamak will have a plasma volume of 840 cubic meters. ITER means International Thermonuclear Experimental Reactor. The acronym also stands for a path in Latin, as ITER could be the way to a new clean source of energy. ITER should fundamentally advance our knowledge of fusion plasma. It could achieve deuterium-tritium fusion and release up to 10 times more energy than it would take to ignite it. The data scientists collect during its construction and operation will be crucial in the planning and construction of the first fusion power plants, which could start supplying electricity to the grid as early as 2050. It should be launched in 2026, but plans for its construction date back to 1985. During the Geneva Superpower Summit, General Secretary Gorbachev of the former Soviet Union proposed to US President Ronald Reagan international cooperation in the search for a new, clean energy source. Eventually, 7 members, China, India, Japan, South Korea, Russia, the United States, and the European Union, cooperated to build a fusion reactor. Construction is underway near Saint-Paul-de-Durance, southern France, close to the Cadarache Research Center. Let's take a closer look at ITER. Its goal will be to achieve a fusion reaction between deuterium and tritium. Deuterium is an isotope of hydrogen easily isolated from ordinary water. Rare tritium will be produced for ITER by CANDU reactors. But for deuterium and tritium to fuse, 2 things will be needed: keep them in place and heat them to 160 million degrees. No container can withstand such temperatures, so the particles will be held by the torus-shaped magnetic fields. This will be created by 18 giant D-shaped magnets called Toroidal Coils. They're 17 meters high, 9 meters wide, and weigh 360 tons each. Together, they can produce 41 gigajoules of energy and create a magnetic field of 11.8 Tesla. They are made of a special superconducting material, niobium tin, which is brittle and difficult to process but retains its superconducting properties even in intense magnetic fields. The coils are enclosed in rigid stainless steel packages and cooled with liquid helium to near absolute zero temperatures, to as low as 4 Kelvin. The entire superstructure of toroidal coils weighs 3,400 tons. Because the plasma ring tends to expand, it is held at the correct distance from the walls by a set of Poloidal coils. These are 6 giant hoops strung across the toroidal coils. The largest is 24 meters in diameter and so huge that it could not be transported. To manufacture the largest Poloidal coils, a winding facility was built on the ITER site. The coils are made of niobium titanium superconductor and cooled with liquid helium to 4 Kelvin. They are capable of delivering a magnetic energy of 4 gigajoules and creating a magnetic field of 6 Tesla. However, the donut-shaped magnetic field generated by the toroidal and poloidal coils would not be sufficient to hold the charged particles to the hot plasma. Under such a configuration, A particle moving along the inner part of the torus perceives a stronger magnetic field than a particle on the outer side of the torus, and is pushed into regions with a weaker magnetic field and thus out of the torus. To correct this, and keep the particles where they are supposed to be, the magnetic field must be twisted like a wrung towel into a so-called helical shape. The third magnetic field will do that. It is created by an electrical current flowing through the plasma, which is induced on the transformer principle. Current flowing through the primary winding of the transformer induces current in the secondary winding, which in the case of a tokamak is the plasma itself. The primary winding of the transformer in ITER represents the central solenoid. It is a 13-meter high and 4-meter wide structure made up of 6 independently operating coil packs wound from niobium tin superconducting cable. In the center of the stacked modules, a maximum field of 13 Tesla can be reached. Because it uses the transformer principle, ITER is a pulse device. It is planned that pulses at maximum fusion power could last around 400 seconds, and pulses at half power could last more than 3,000 seconds. The plasma confined in a magnetic cage needs to be heated to a fusion temperature of 160 million Kelvin. Initially, it is heated by Joule heat, but at temperatures above 10 million degrees, the resistance of the plasma drops and other heating methods must be used. ITER uses neutral beam injection and ion or electron cyclotron resonance heating. NBI is actually a particle accelerator that accelerates deuterium ions with an electric field. To keep them from being affected by the magnetic field, the particles are neutralized before entering the plasma and then transfer their energy to the plasma by collisions. Neutral beam injectors are monstrous machines sized like steam locomotives, 25 meters long, 5 meters high, and 5 meters wide, with a chimney-like bushing reaching up 9 meters to connect to the openings on the 3rd floor. Each of them is capable of delivering a deuterium beam of 16.5 megawatts with a particle energies of 1 mega-electron volt. The ITER is equipped with 2 heating neutral beam injectors, one smaller neutral beam injector for diagnostic purposes, and has a place for a 3rd heating device if needed. Resonance heating works much like a microwave oven. Radio waves of the right frequency transfer energy to the particles in the plasma and heat them up. The particles then transfer energy to each other by collisions. The ion cyclotron resonance heating uses a frequency of 40 to 55 MHz to heat the ions. 2 transmitting antennas are about 3.5 meters long, with a cross-section of 2 by 2 meters and a weight of nearly 50 tons. The system delivers 20 megawatts of energy to about 1 gram of plasma, thus raising its temperature very high and very quickly. Electron cyclotron resonance heating heats electrons using a frequency of 170 GHz and supply an additional 20 megawatts of energy to the plasma. 160 million degrees of hot plasma gripped by magnetic fields cannot be in contact with the atmosphere. The whole process is therefore enclosed in a vacuum chamber. It's a giant stainless steel donut whose cross-section is elongated vertically into a D shape. Its outer diameter is 19.4 meters. It is over 11 meters high and weighs 5,200 tons. From an internal volume of 1,400 cubic meters, the plasma occupies 840 cubic meters. The walls of the chamber must be resistant to high temperatures and act as a shield against strong neutron fluxes. On the inner side of the chamber, there is a so-called blanket, consisting of massive neutron shielding modules on which replaceable first wall panels are mounted. They will directly face the plasma. To withstand the high temperatures, their surface is made of beryllium. Underneath is a copper heatsink and stainless steel support structure. These tiles resemble carbon tiles which protected the space shuttle during the descent through the atmosphere. But ITER tiles will have to withstand several times more intense heat flux than any space shuttle. A piping is routed through the blanket to circulate the cooling water. ITER will be the world's first tokamak with an actively cooled blanket. A divertor keeps the plasma in the ITER tokamak clean. The particles from the peripheral regions of the plasma are guided by magnetic fields that cross into an X shape next to the divertor and end directly on the divertor walls. From there, the impurities are extracted by powerful vacuum pumps. To withstand the extreme heat load, the divertor cassette is covered with tungsten plates actively cooled by water flowing in pipes beneath them. One divertor cassette weighs 8 tons. ITER has 54 of them arranged in a ring at the bottom of the Tokamak. They will be inserted into the chamber after it is completed, through the port and seated with sub-millimeter precision. The inner surface of the vacuum chamber, facing a plasma of 160 million degrees, will therefore be heated to hundreds and sometimes even more than 1,000 degrees Celsius. But just a few meters away, superconducting coils cooled to just 4 degrees above absolute zero will be located. Fortunately, there is an effective way to separate such large temperature differences over such a small distance: vacuum. The best insulator in the universe to reduce the heat transfer between the chamber and the coils to a minimum. The entire chamber, including the magnetic coils, is enclosed in a giant evacuated vessel called a cryostat. In principle, this is the largest thermos in the world. It's a giant steel cylinder 30 meters wide and 30 meters high, weighing 3,850 tons. Its internal volume, in which an ultra-high vacuum will be created, is 16,000 cubic meters. ITER construction is expected to be completed in 2026, when the first plasma will be ignited. This will begin the scientific life of ITER. Gradually, individual systems will be tested and commissioned. The temperature of the plasma will be increased, the discharge length will be extended, and the first scientific findings will emerge. In 2035, experiments with a mixture of deuterium and tritium and the first ignition of thermonuclear fusion should take place. This should, if all goes to plan, release 500 megawatts of fusion power and produce up to 10 times more energy than will be used to ignite it. Subsequently, a series of experiments should accumulate enough scientific knowledge to enable the world's first commercial thermonuclear power station to be constructed and started up. With ITER, thermonuclear fusion energy is one step closer.